Hey guys, welcome back. This week we're going to talk about Unit 4, which is mostly Earth science. We're going to start by talking about plate tectonics, and that's basically like the shell of the Earth and how it's broken into parts. And so we'll look at those boundaries, but first we're going to watch this video that tells you all about plate tectonics.
Grow. This is due to plate tectonics, or the large-scale movement of Earth's continents. The motion occurs within the top two layers of the Earth's mantle, the lithosphere and asthenosphere. The lithosphere, which includes the crust and uppermost mantle, comprises the land around you. Beneath the lithosphere is the asthenosphere, the highly viscous but solid rock portion of the upper mantle. It's between 80 and 200 kilometers below the Earth's surface. While the asthenosphere wraps around the Earth's core as one connected region, the lithosphere is separated on top into tectonic plates. There are 7 primary tectonic plates that compose the shape of the planet we know today. Like the other smaller tectonic plates, the primary plates are about 100 kilometers thick and are composed of 1 or 2 layers, continental crust and oceanic crust. Continental crust forms the continents and areas of shallow water close to their shores, whereas oceanic crust forms the ocean basins. The transition from the granitic continental crust to the basaltic oceanic crust occurs beyond the continental shelf, in which the shore suddenly slopes down towards the ocean floor. The South American plate is an example of a tectonic plate made of 2 crusts, the continent we know from today's map, and a large region of the Atlantic Ocean around it. Collectively comprising the lithosphere, these plates are brittler and stiffer than the heated, malleable layer of the asthenosphere below. Because of this, the tectonic plates float on top of this layer, independently of one another. The speed and direction in which these tectonic plates move depends on the temperature and pressure of the asthenosphere below. Scientists are still trying to nail down the driving forces behind this movement, with some theories pointing towards mantle convection, while others are examining the influence of the Earth's rotation and gravitational pull. Though the mechanics have not been sorted out, the scientific community agrees that our tectonic plates are moving, and have been for billions of years.
Okay, the first type of boundary is convergent. This is where they come together, and in this case form the Himalayas. The second type is divergent, where they go apart, and in this case they form a rift valley. And the last is transform boundaries, and like the San Andreas Fault. And so we're going to watch a quick clip of that movie.
Oh my God.
The Earth will literally crack open, and you will feel it on the East Coast.
Okay, so that was a little dramatic, but now we need to look at soil formation. And we already talked about that with primary succession, so now we're just going to look at the layers. The first layer is the O horizon, or the organic, and beneath that is the A, and that's the topsoil, and so you can see lots of different minerals and living things there. As we go down, you can see they are different zones, but not all soil profiles have all of them. R being the bedrock, and that bedrock is where soil is formed with the help of lichen and weathering and those sorts of things. So the arrows, zone of leaching, is just water infiltrating down and bringing things with it. Zone of accumulation is where we find a lot of different minerals like iron. If you look now, you can see that I finished the coloring sheet, and so red being the least permeable, they're smaller, and so when they stick together, it's like they form a barrier. Silt allows, especially mixture, allows for more filtration of water, and then sand is largest, so it allows for the fastest and most water to go through. And here's where it matters. Remember that we're looking at the parts that make up the soil, whether it's clay, sand, or silt, to see how we can use that soil. And so loam is kind of the sweet spot. It allows water to get to the roots, yet not to just go straight through. And so we use that triangle to determine what we should plant. Okay, now we're going to talk about the layers of the atmosphere. We will start with the troposphere, and that is where weather occurs. The greenhouse effect is in this layer, and that's because when the UV rays come in, gases like water vapor and CO2 can actually trap it. And so they trap in that heat that's reflected off. We can see planes flying here, In the next layer, we have the stratosphere, and it is important because it contains the ozone layer, which is like our sunblock. And so you can see there are different types of UV rays that are coming from the sun, and and weather balloons can be there. And so you have UVC, UVA, and UVB, and some UVB does come through. UVB is going to cause the skin cancer and the sunburns, while UVA, the aging and the wrinkling. The next layer is the mesosphere, and meteors burn up here, and we know that some rockets can go through it, and it becomes cooler until it gets hotter in the thermosphere, and it gets super, super hot, like over 1500 degrees Fahrenheit. We can see spacecraft here, and satellites can orbit here, and the aurora borealis and all those things are kind of looking at them right there. Beyond that, there is the exosphere, and so that's kind of like that space between Earth and the layers of our atmosphere. Okay, now we're going to look at wind patterns. Wind is driven by solar radiation, and we're also going to look at ocean currents, which are determined by ocean floor topography and also different densities, and the top layer can be affected by the wind. So watch this video for some really great visuals and terms.
To look at the patterns of surface currents all over the Earth, you'll see that they form big loops called gyres, which travel clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. That's because of the way the Earth's rotation affects the wind patterns that give rise to these currents. If the Earth didn't rotate, air and water would simply move back and forth between low pressure at the equator and high pressure at the poles. But as the Earth spins, air moving from the equator to the North Pole is deflected eastward, and air moving back down is deflected westward. The mirror image happens in the southern hemisphere, so that the major streams of wind form loop-like patterns around the ocean basins. This is called the Coriolis effect. The winds push the ocean beneath them into the same rotating gyres, and because water holds on to heat more effectively than air, these currents help redistribute warmth around the globe. Unlike surface currents, deep ocean currents are driven primarily by changes in the density of seawater. As water moves towards the North Pole, it gets colder. It also has a higher concentration of salt, because the ice crystals that form trap water while leaving salt behind. This cold, salty water is more dense, so it sinks, and warmer surface water takes its place, setting up a vertical current called thermohaline circulation. Thermohaline circulation of deep water and wind-driven surface currents combine to form a winding loop called the global conveyor belt. As water moves from the depths of the ocean to the surface, it carries nutrients that nourish the microorganisms which form the base of many ocean food chains. The global conveyor belt is the longest current in the world, snaking all around the globe, but it only moves a few centimeters per second. It could take a drop of water 1,000 years to make the full trip.
Okay, watersheds you know about. These are all of them throughout the state of Texas, and here's a quick clip on a definition.
Watersheds are areas of land that water flows across, through, or under before draining into creeks, streams, rivers, lakes, or oceans. We all live in watersheds.
Okay, here's another familiar concept, and that's seasons. And we know how they are formed, but this video urges you to consider the angle at which the UV rays hit the Earth.
The Earth spins on its axis at a fixed angle of about 23½ degrees. And as the Earth goes around the Sun once every 365.25 days, this axial tilt, or obliquity, changes the exposure of the Sun's radiation that different parts of the Earth experience at any given time. So starting in a couple weeks, the northern hemisphere will tilt toward the Sun, and people will break out the iced tea and sunscreen, while the southern hemisphere will point away and begin bundling up for the relative darkness of winter. But here's the thing, lots of people think that the hemisphere that's tilted toward the Sun experiences summer because it's closer and therefore hotter, which is just false. In fact, those of you in the northern hemisphere might be surprised to know that the Earth is actually 5 million kilometers closer to the Sun in January than it is in July. So the difference doesn't have to do with your hemisphere's proximity to the Sun, it has to do with the angle of the Sun's rays that it receives. Let's say this piece of paper is the Earth's surface, and this flashlight is the light of the Sun. When the light shines directly onto the paper at a right angle, you see a perfect illuminated circle. But when I tilt the flashlight, that circle stretches into an ellipse. So the same total amount of light is hitting the paper, but it's now more spread out, so the light energy per square centimeter is reduced. This effect, combined with the fact that higher sun angles result in longer days, means that more energy is heating your hemisphere in the summer and less in the winter. But if you're near the equator, you probably barely notice any seasons at all, since you get roughly the same amount of sun year-round. The poles...
Alright, and so here's the last topic. And El Nino is kind of somewhat of a beast. Scientists don't know everything about it yet, but basically it occurs every 2 to 7 years, and it is a weakening of normal trade winds, and it causes havoc on fisheries, and it causes intense weather events like droughts and floods in different parts of the world. La Nina being the opposite, and this is, it does similar things where it changes what fish are available and also changes weather patterns. So watch this video, which gives an excellent explanation on top of great visuals.
But what is El Nino and how does it happen? Firstly, we need to know what's normally happening in the tropical Pacific. This vast stretch of ocean sees consistent winds called trade winds that blow from east to west. These winds push warm water near the surface in their direction of travel, so the warm water piles up on the western side of the ocean around Asia and Australasia. On the other side of the ocean, around South and Central America, as the warmer water gets pushed away from the coast, it's replaced by cold water which is pulled up from deeper down in the ocean, a process called upwelling. This creates a temperature difference across the tropical Pacific, with warmer water piled up in the west and cooler water in the east. Warmer water adds extra heat to the air, which causes the air to rise with more vigor, and it's this rising air that creates an area of more unsettled weather, with more cloud and rainfall. That rising air in the west sets up atmospheric circulation across this part of the world, with warm, moist air rising on one side of the ocean and cooler, drier air descending on the other. This circulation reinforces the easterly winds, so this part of the world sits in a self-perpetuating state until El Nino begins. If conditions are right, tropical Pacific weather systems, or slow changes in the ocean around the equator, can set off a chain of events which weaken or even reverse the usual trade winds. With weakened trade winds, there's less push of warm surface water to the western side of the ocean and less upwelling of cold water on the eastern side. This allows the usually colder parts of the ocean to warm, cancelling out the normal temperature difference. Because the area of warmest water moves, so does the associated wet and unsettled weather. This changes rainfall patterns over the equatorial Pacific, as well as the large-scale wind patterns. It's this change in winds which has a knock-on effect, changing temperature and rainfall in locations around the world. The main impacts are around the tropics, where you see an increase in the risk of floods in Peru and droughts in Indonesia, India, and parts of Brazil. But virtually wherever you are in the world, El Nino has the potential to affect you directly via the weather or indirectly via socio-economic impacts. There's another impact from El Nino which happens because of all the extra heat at the surface of the tropical Pacific. This releases vast amounts of energy into the atmosphere, which can temporarily push up global temperatures. This is why El Nino years often feature among the warmest on record. Each El Nino event is different, so the global impacts can change. You can find out more about the differing impacts of El Nino on our website. El Nino peaks around Christmas time and lasts for several months. It can die back to neutral conditions, but sometimes reverses into La Niña. This is the flip side of the oscillation, which sees a strengthening of the normal trade winds. This pushes the warmest water to the far western part of the tropical Pacific and increases the upwelling of cold water in the east. This cooler water extends out from the coast of the Americas towards the central part of the ocean. La Niña also impacts global weather and tends to have opposite effects to El Nino.
Okay, complete the viewing guide, submit it to me, and complete day 2's assignment as well. I hope you have a great day. I miss you. Talk to you soon. Bye.